and let him take over here. Thank you, Marc, for sharing your time and talents with us.
All right. Well, yeah. Thank you, everybody, for for being here, for inviting me, allowing me to be here. You're lucky that Bronwyn is timing this and trying to limit me to an hour, and so I'll hit my little timer here because I've been known to do this for like 3 to 5 hours when we do public outreach. So it is something that I'm excited about. So I like having the opportunity. I like meeting people that want to know more and or maybe get bit by a similar bug or the same bug. So this is a slide. Hopefully everyone can see it. Hopefully if you end up having trouble either hearing me or seeing what I'm trying to present, especially when we get to 2 short videos, please speak up so you don't miss it. But the main thing I want to point out here, this image comes from 2007. So I was in Manicouagan impact structure in Quebec. And you note the elevation I'm at. We'll kind of look at this again in another slide later. But the thing I want to hit here in the title is, well, what do we mean by hypervelocity impact cratering? What do we mean by, I'm not trying to just sound cool, but what it really is referring to is a velocity greater than 3 kilometers a second. So that's not a minute, that's not an hour, that's very high velocity, very, very quick. So we'll talk about velocity again. And then let's see here. Another thing I want to do before we get started on the proper discussion is talk a little bit about inspiration. So this is a slide that the 3 photos on the left, basically this, let me try and do my laser pointer right here. So this is a church in Nordlingen in Bavaria, southern Germany, and it's made of quarried stone from a local quarry. And I was watching an educational program in the 1980s, and it had Gene Shoemaker and his wife, Carolyn. He's a famous geologist. He's also done some astronomy. And he was close to the building, pointing at one of the building stones, similar to this image down here. This is a photo that comes from Dr. Mark Schmieder. He's also an impact scientist. And so this comes from one of those building stones. And you can kind of see these dark blebs in here. Some of them have kind of a fluidal shape to them. And Gene was pointing out that you could just look at this rock and see that it was the result of a hypervelocity impact from an asteroid striking the Earth. And that gripped my imagination to think that he knew so much looking at that stone to understand that that was the what caused it. So another thing in the 80s was seeing some images of things like Voyager 1. So this photo on the right, it's kind of a poor quality if you look at the color and the resolution. But for back then, this was amazing that this is the moon Io. It's one of the many moons of Jupiter. And then they noticed this footage here of a volcano erupting hundreds of kilometers above the surface of the moon Io. That was another thing that excited me. So I'm just asking you to think about the things that you're passionate about and give yourself permission to not talk yourself out of them. If you're interested in that kind of stuff, learn more about them like you're doing right now. So an overview of what we're going to talk about, you probably saw this in the advertisement online. We're going to talk about why impacts are, why studying them is important to us as a society, not just to researchers. Learn a little bit about how they form on the surface of the Earth. Talk about, there's 2 main types. We'll review that. We'll look at how many have been discovered and proven on the surface of the Earth. We'll review briefly a near miss that happened in 2013. We'll look at a brief video to answer the question, do asteroids still pose a threat? And then we'll end up with the last thing we'll cover. I'm at Arizona State University. I did my PhD at University of New Brunswick in Canada. But I got involved with Arizona State University, and the department I'm in is the School of Space and School of Earth and Space Exploration. The lab I worked with is now known as Group 18. So they've done a lot of dating of terrestrial impact structures. And so we'll just talk about a couple of examples, one of them being Chesapeake Bay. We'll kind of lightly review some of that. So let's kind of get started here. And that's not doing what I want. There we go. So why are impact craters important to research and to society? Well, you may understand that the planets were formed from material in a disk around the sun as objects were colliding and getting larger and getting more gravity. and accreting more material. So in a way, we're all kind of like recycled asteroids in a way. So it key in the formation of all plants, but also impacts are hazardous to life on Earth. So if you look at my background, this is a fairly small crater in Arizona, but it was still hazardous to life on a local scale. We'll briefly look at the 65 million year old Chicxulub impact structure, which was hazardous to life on a global scale. So also impacts are used to estimate planetary ages on other bodies, things like other moons or other planets within the solar system. And then in large impacts, subsurface materials can be brought to the surface. So there's mineralogy that can be shown on the moon, that mineralogy from more like a mantle level were brought up to the upper crust, exposed at the upper crust. And you can see things that you would normally not be able to without drilling down. So here's a image of a Google Map satellite image. So we see here's Newfoundland and Labrador. Here's the Gulf of St. Lawrence. Quebec City is down here, kind of off the map. And then part of Quebec is right here. So I want you to focus on this right here so that you can see this from orbit above Earth. And this is the Manicouagan impact structure. And I keep doing that. There we go. My area of interest, this is a false color digital elevation model. And you can see a little bit closer now. So this blue, this flat blue is actually the lowest elevation, and it also represents water. So it's a reservoir. So we see rivers coming into the reservoir, and there's a dam south of this mapped location, and that's kind of why it's all filled up with water. And then the pink here is the highest elevation, and what you just kind of want to focus on is this little ellipse here. So that was where I did 6 months of field work studying the central uplift at this impact crater. Now here's a helicopter taking our stuff out at the end of one of our field seasons. And then this is a false color map. This is kind of like a shaded relief map on the upper part. And you see the different colored patterns. Different colored patterns represent different kinds of rock types in my area of research for my PhD. But what I'm really trying to point out here is, so that first picture you saw on the first slide was taken here, August of 2007. And then I've broken down locations for where we've done different camps. So the dots mean that's where samples were taken or notes were taken. So there was actually like 3 different camps for 2008 for that field season. And so you get the idea. I'm just trying to show you how much area I covered in that region. So let's see. This image on the lower left is showing outcrop of rock is really good in places. And then the lower right image is showing it's not like that everywhere. One of the interesting things being there late in the summer that first year in 2007 was the blueberries were ripe. And so here we see a mother bear and one of its cubs, and here's the mother bear and the 2 cubs. They were pretty close, and they're enjoying the blueberries, and so were we as we did our work. And then fascinating, while we were there, this seagull out in the middle of nowhere, just one seagull for about 10 days was gobbling ripe blueberries as we did work. And then after about 10 days flew off and never saw them again. So how do impact craters form on Earth? Here's another kind of snapshot from Google Maps. And so we've been talking about this. A lot of people in the audience have been here. So Winslow to the east, Flagstaff to the west. It's about 58 miles separating the two. You can get to each of them through I-40. If you go south of I-40, you see this bright patch, and that is what used to be known as Meteor Crater or Behringer Crater. And so this panorama here, the lower image, comes from a visit that here at Arizona State University, Professor Tom Sharp, we had some visiting scientists come in and they wanted to take a tour. So we took them up there and we toured the rim. When we look at Behringer Crater or Meteor Crater from above in an aerial photo, we see this is the road that you come in, this is the parking lot, and then here's the visitor center. You'll notice that this crater isn't quite circular. It's kind of rounded corners of a square. But the Behringer impact crater itself is fairly young. It's very pristine. It's in great condition, partly because it's so young. You may not think that 50,000 years is not a lot of time, but in geologic terms, for, the Earth being 4.56 billion years old, that's pretty young. And so what I want to do here is I want to look at this. It's a brief video courtesy of Dr. David Crating. He's like the crater scientist for Behringer Crater. He's connected to the Behringer family who runs the local site. And so like scientists can't really get in there without going through Dr. Crating. And this is a good video that talks about how the crater formed.
About 50,000 years ago, a nickel-iron asteroid approximately 30 to 50 meters across, traveling around 15 kilometers per second, hit the grassy plains in what is now northern Arizona. The energy of the collision ejected material from below the surface and away from the point of impact, leaving behind the Behringer meteorite crater. This crater, nearly 180 meters deep and 1.2 kilometers across, is the best preserved impact crater on Earth.
Okay, so I like that video because it does a nice job of panning the whole crater. As you can see, it's fairly large compared to the size of a human being, but it's not so large you lose the sense of the scale of it. So if we look back at that photo that we looked at a little while ago, and I do a cartoon of it, and let's kind of review what he said. There's not a lot of information in that brief video, but he said that the projectile was about 40 meters in diameter. So that's what I've got with this little red circle here. But it created a 1.2 kilometer wide impact crater. So how can you take such a small object and create such a large crater? And he said, the key is the impactor velocity, which in this case, he's guessing was about 15 kilometers a second. So like I said, that's not a minute. That's not, not per minute, not per hour. That's quite a high velocity. We can look at another diagram here. Dr. Crating works at the Lunar and Planetary Institute in Houston. This diagram comes from the Lunar and Planetary Institute in Houston. And we see here that it's showing us two bits of information. It's showing us asteroid velocities and comet velocities on two different bodies. Blue represents the moon, orange represents the Earth. So if you look at the y-axis, as you go up, you're just going up in the number of impacts on each body. If you look at the x-axis up top, it's in impact velocity for miles per second. And if you look at the bottom, x-axis is in kilometers per second. So really what we want to do is we kind of want to follow this orange line up here to this peak. And we see the average impact velocity for Earth for asteroids is about 12 miles a second or about 17 kilometers a second. So that's pretty quick. So, cosmic velocity. You can also take a quick peek here. Short period comets on the Earth is about 29 kilometers a second or 50 kilometers a second for long period comets. So the impact cratering process is normally broken down into three different stages. You can think of it's the contact and compression stage is stage 1, excavation is stage 2, and modification is stage 3. So what I've done is this is kind of an older illustration from a textbook, but it's still kind of one I like it for it being concise and not being an actual animation. So if we start in the upper left, we see the projectile hitting the surface of the Earth. So that's the start of our contact and compression. A great amount of pressure is created on the projectile and that locality of the target rock. And as it does that, it generates a shock wave that transmits out into the target rock quicker than the excavation can take place. And as we move along, we see that shock wave speeds away. And as it does so, it weakens. We see material starting to be excavated and ejected out of what is going to be a transient cavity. We see again, the shock wave has made it further away and weakened. And we have this ejecta curtain coming out. It's going up, it's not going down yet. Then there's a point where the excavation stage ceases, gravity takes back over, the ejecta starts to fall back down, and depending on the size of the crater, we can end up with different morphologies of the final crater. So here you can kind of see there's a little bit of material that's upturned in the middle. So that kind of leads us to our next question, and that is, let's review the two basic types of impact craters. So we need to kind of like think about the scale. So this is a diagram. I've kind of shaded off part that I don't want you to pay attention to now. I just want to look at the upper part and think about, so if you look at the D right here, if the diameter of the final crater is less than about 3 kilometers, depending on what the target material is, we end up with a simple bowl shape. So this is kind of like a cutaway view. So you can kind of see that shape. The blue material is material that was ejected out of the crater. Red material is material that fell back into the crater. This doesn't necessarily mean that it was melted or that it was all melted. It will most likely contain some melt, but it's not meant to represent total melt. So here's a beautiful example of a simple crater on the surface of the moon. This is known as Linne, L-I-N-N-E. It comes to us from LROC folks here at Arizona State University, but they're associated with NASA and Goddard Space Flight Center. And you can see that beautiful bowl shape. So that's 2 kilometers in diameter on the surface of the moon. So we can now answer what type is Behringer crater or Meteor crater. It's a simple crater. And then if we look at that lower part of the diagram, if we get to diameters greater than about 3 kilometers in diameter, we see a much different resulting shape. So this is a complex shape. Notice that the diameter, which is right around here, the ratio of the diameter to the depth is quite different. Up here, the diameter was much more similar to the depth, much more 1-to-1. So here we end up having a lot more shallow depth compared to the diameter. So blue again represents material that was ejected out. Notice the uplifted portion here in the center that's poked through the red material. Also, in the case of larger craters, we can get a large volume of the target rock actually turned into coherent melt sheets. So it's like a lake of lava that can sit, hot and molten for thousands to tens of thousands to hundreds of thousands of years, depending on how large the crater is. So Manicouagan actually had a coherent melt sheet. Most of the central island is covered in melt that in places is more than hundreds of meters thick. If we want to look at a nice example on the moon, so you've probably looked at the full moon with binoculars at some point, or hopefully a telescope, and you would recognize this beautifully whitish rayed impact crater known as Tycho. So this is material that was ejected out of that crater. So if you kind of think of how bright it is compared to the other material is more weathered. And so this is younger. And then if we look at this more closely this is a mosaic of images that comes from the LROC team, the Lunar and Reconnaissance Orbiter Camera team. So Professor Mark Robinson works here in the School of Earth and Space Exploration here at ASU. So there's a wonderful image. And now we can see that terraced rim, with the different elevations along the rim. And then we see this beautifully centrally located central uplift. Long dimension here is about 15 kilometers. And then we can now classify the Manicouagan impact structure is an 85-kilometer wide complex crater on Earth. So I'm standing on the central uplift. So that's part of how we also know. And then the red dashed circle is just meant to show you this reservoir is an interior feature and it's not the crater diameter. And this is another example. This is a good reason for my title of this presentation isn't very good, because we have a lot of impact craters that don't look like a crater anymore on the surface of the Earth. Manicouagan, to an extent, is like that because glaciers have modified since the impact occurred what remains. So it can be a little bit confusing to look at. So sometimes it's better to call these impact structures and not impact craters, just so there's not confusion as to they aren't always crater-like. So how many impact craters on Earth? Do I have any guesses? Okay, just under 200. And so there's different websites out there that you can kind of like check this kind of information. The group I was with in the University of New Brunswick, Planetary and Space Science Center, run by John Spray, they run the Earth Impact Database. So if you go to Google and you type in Earth Impact Database, you can actually learn more about craters. So if you want to learn more about Chesapeake Bay, go to Google, type in Earth Impact database, Chesapeake Bay, and you'll see recent research that's been done on it as listed titles of journal articles and things like that. It'll tell you the approximate age, the diameter, the target rock, suspected projectile, things like that. But this map comes from Dr. Ludovic Ferrier at the Natural History Museum in Vienna. He's also an impact researcher. He's actually discovered at least one and or proven what was already kind of identified as a potential impact crater. And so red dots here are the location. They have nothing to do with the diameter or size. And you can see there's areas where there's not very many, and that's partly because they're remote. And then there's areas where there's quite a few, and that's because heavily populated. But part of it might also be the surroundings. If you have a lot more sedimentation and erosion, it might be harder to find them. If you have a lot of vegetation, it could be harder to find them. And then there's also things like a bias where places like Canada actually employed people to go looking for them. And so anyway, he also listed totals by continent here.
Hey, Mark, quick
Yes.
question from the
Yep.
from the gallery was Justine noticed no craters in the ocean.
Yeah, okay, so yeah, that's a good point. It doesn't mean they don't exist. It just means that I don't know of any offhand that have evidence for them. So in a way, you can kind of think of Chesapeake Bay is partially underwater. And so what we know comes from drill core. So it's stuff we can get our hands on. I'll show you some other examples that come from, some of the science that we get comes from drill core because you can't get there because like it's in a lake. And then the other example would be partly Chicxulub. So Chicxulub, part of it is land and part of it's underwater. But that's a very good thing to note. And so there's a lot of impact craters on Earth that have not been discovered or proven. Now, if we look up at the moon, if we look at an image like this, we can't count how many impacts are up there. So 200 on the face of the Earth, what is, I've kind of alluded to some of it. So some of the reasons for this is because we have an atmosphere, we have a lot of water, we have a lot of weathering. So we have ice and thaw, freezing and thawing. And we also have plate tectonics. We have a warm Earth that's geologically active. So we have movement of plates and we have recycling of crust. So an interesting thing, since she brought up the idea of the ocean floor, another reason we don't find them very often on the ocean floor, it's not just because they're difficult to get at, but it's because the ocean floor is quite young compared to the older continental crust. So I don't mean that to be a blanket statement. I'm just saying continental crust can approach the age of the planet, but oceanic crust doesn't get older than about 200 million. And that's not very old for a 4.56 billion year old planet. So a lot of ocean craters have been erased because of the recycling of the crust. So they've either been erased or they've been filled in is normally what happens. So what can we use as valid proof? So some people have already kind of like started to think about this or mention it in the chat. Well, we need to look for shock metamorphic effects, and that's normally seen in minerals can record it, and rock surfaces can record it. So if we look at this image right here, this comes from French and Kerbel's work in 2010, where they actually published an article to try and, there were so many people excited about trying to find impact craters that they weren't doing a very good job of trying to prove impact craters. And so they tried to kind of help provide ideas of, well, if you find, so normally a quartz crystal is going to look pretty clear, and you're not going to see, let's see here, you're not going to see these linear features in here. I put two white lines on here to help you see there's kind of two sets of planar deformation features in this quartz crystal. This is similar to what they found in some quartz grains associated with Chicxulub, but this is actually ejected material from the Manson impact structure in Iowa. And then, so this is great if you can, if you can find such small grains, look at them under a microscope, and then know what you're doing to actually you actually have to tally these. How many did you see? What percentage? And keep records and look at more than one grain, you know, if you're going to really be systematic about it. But we also have things like on the lower left side of this image here is, let's see, I'm trying to get, there we go. This is what is known as a set of shatter cones. So it comes from an impact crater in southern Germany. And the target rock there is a fine grained carbonate rock. And when I showed you those little images of the shock wave passing through the target rock, in many cases, it actually fractures the rock in a way that if you go find a rock in this area and you have a hammer, you may pick it up and it may look very unappealing or very uninteresting. You hit it and it will break along that fracture zone and you'll see this beautiful shape. So you see this like narrow part, the top of the cone here, and then it gets wider. And then we see this beautiful feathered texture, or it's also known as horsetailing kind of texture. And this is something that you could see in hand sample. You don't need special chemistry, or you don't need like a scanning electron microscope. You don't need a lot of money. If you properly identify this, you now know that you are in an impact structure that was caused by hypervelocity impact. So this is a diagram that tries to compare some of those shock effects, shock metamorphic effects, to normal crustal metamorphism. So on the y-axis going up, we have increasing temperature in Celsius, x-axis going to the right, increasing pressure. And then if you look, this blue envelope right here is meant to kind of show the limits of what you would normally see in rock that has undergone normal crustal metamorphism. So if you're in a mountain building area and you see a metamorphic rock, it probably hasn't seen temperatures above 1,000 degrees Celsius, and it hasn't seen pressures above about 4 gigapascals. But so looking at that shock quartz grain from that earlier image, that little rainbow colored quartz grain, you start to get planar deformation features at about 5 to 6 gigapascal. And so you're now beyond what crustal metamorphism can do. If you look at the shatter cone, it's at about 3 to 10 gigapascals. And then other things, you know, there's other ways to identify it. We can also look at this idea here where they've got these dashed lines. So for quartz, it can be transformed into coesite or it can be transformed into stishovite, depending on pressure. So this can happen within the surface of the Earth, but you don't normally find it at the surface of the Earth like that. And so what's interesting is quartz, coesite, and stishovite all have the same chemistry. They're all the same chemical makeup. They're all silicon and oxygen, because they're the same. That's the product they are. But we can change the structure of them by subjecting them to higher pressures. So what this little set here is, there's a piece of equipment known as a Ramen Spectroscope. It uses laser light that you can direct at a mineral. And depending on how the laser light interacts with it, it will give you a spectrum. So this is a single spectrum that is characteristic of the response for quartz. So, and then when you look at something that's been subjected to higher pressures, so we're saying between 3 and 10 gigapascals, we get a different spectral response that's indicative of it. Now it's coesite, it's not stishovite, and the same thing for stishovite. So that's kind of what that is. It's saying, well, in hand sample, it may look like quartz, but under something like a Raman spectroscope, it would give us these kind of indications. If we look at shatter cones at Manicouagan, these aren't near as pretty looking as what we saw from Steinheim, but you can kind of see like an inverted cone here. The rock is more coarse grained and it's more weathered. So that's the two reasons it doesn't look as good as the other ones. And then you can also see one here. We also found smaller ones in this area. So we know we were looking at shatter cones, and then you see the hammer for scale. Here's a network of shock veins at Manicouagan. Left side shows you these white little kind of linear, but not quite straight, wispy things that I drew a sketch of on the right to kind of help you see. If we take a hammer and break one of those off, we can get a piece kind of like this in places. This came from Manicouagan. We can see mineralogy on this side is quite different than this side. A lot of darker mafic minerals here. but we see this shock vein that splits the two, and we can see there's area where this white shock vein got kind of chaotic and went in different directions. But if we make a thin section out of that and look at it under the scanning electron microscope, this right here, this lower left image is under the scanning electron microscope. This is the melt vein out here, this gray area. And then this region here, these little brighter nodule looking items, that's actually quartz that was converted to stishovite. And right here is a scale bar to help you out. So this bar is 30 microns long, and it takes 1,000 microns to make a millimeter, if that helps you. And then we looked at this with Ramen spectroscopy, and this is the spectrum we got from it, which is indicative of it is stishovite, which means it was subjected to pressures of about 15 gigapascal. So we can now take a quick peek. You know, Earth has had more than one near miss, but for the sake of time, you know, we can talk about more if you want to during the question part. Many of you may remember 2013, Chelyabinsk, Russia. If you haven't seen the footage, it's wonderful. Just go to Google and look up Chelyabinsk dash cam, and there's a lot of entertaining stuff there. This upper left image does come from dash cam. You can see it's daylight and how bright the fireball is. It doesn't look like it's full daylight because the cars have their lights on, but it's still quite bright. And then, so there was a pressure wave, there was a shock wave associated with this hitting the atmosphere, and it caused damage. So this lower left image is showing that, you know, people got hurt, they got sent to the hospital. But you got to understand that if we go back to the upper left image, that asteroid, when it hit the atmosphere, when it first broke into the atmosphere, it was going at cosmic velocity, but the projectile wasn't coherent. It didn't stay in one solid piece, and it didn't maintain that cosmic velocity. It got slowed down by the atmosphere. It broke up into many pieces. One of the larger pieces broke through this frozen lake. It was retrieved here. So yeah, you wouldn't want to get hit by something like that, but it did not hit at cosmic velocity and create an impact crater like that in Behringer Crater in Arizona. So do asteroids still pose a threat? This is a very short video that comes from JPL. And let's see here. So animation represents increased count between 1999 and 2018 of known asteroids. Blue represents near Earth asteroids, ones that can cross the orbit of Earth. That's a problem. And then the later part shows in orange those between. So this is the orbit of Jupiter. I can't show it because the outside orbit is Jupiter. The next one, red, is Mars, and then Earth, Venus, Mercury, and Sun at the center. And you see the count increase. It's important to know that this isn't to scale. These aren't objects to scale. They're just trying to show you location. And then, yeah, at the end, there's quite a few that could cross and or impact with the Earth. There's other variations on this kind of video. It's worth checking out. But for the sake of time, I like that one because it's pretty short. So let's take a brief look at the direct hit from 65 million years ago. So that's Chicxulub impact structure in the Yucatan. You want to check out a pretty neat book it's not a difficult read. It's not really a scientific read. It's T-Rex and the Crater of Doom was one of those books that pulled me in. It was more about describing what was happening. I think it was in the 80s when this crater was first getting determined, first getting discovered. You know, different people knew different bits of the puzzle. Not everyone agreed, but yeah, it's a pretty neat, intriguing story. And then, so the impact crater, the resulting impact crater is quite large, 150 kilometers in diameter. The projectile is quite large, 10 kilometers in diameter. You know, when you look through scientific materials, you're going to see variations. You're going to see some people want to call it 200 kilometers, or one, you know, person wants to argue it's only 125 kilometers. You have to take that with a grain of salt. But these are fairly, these numbers come from Earth Impact Database, so I'm pretty comfortable with those. So left side image here is a gravity anomaly map. Like I said, this is not something you can just like get into a submersible and go visit per se. It was buried pretty quickly. Someone was mentioning they just saw a show about it took drill core in another part of the impact structure to learn more. What was initially learned was mostly learned from drill core that was from oil and gas. So it wasn't really scientific research. They were trying to kind of like double dip. Oil and gas companies, they go and take cores and try and figure out what oil and gas is. And then scientists were trying to look at that material. They were finding shock metamorphic effects, but this recent drilling was actually like $10 million. I think it was $10 million was spent just for getting scientific drill core that they wanted to preserve and learn as much as they could. So anyway, this is a gravity anomaly map that's done in false color. It's not really the bottom depth, but it shows variations in gravity that show you the shape of the crater, and that's a famous image. It comes from Sharpton and others. He was working at Lunar and Planetary Institute. That's where the LPI comes from. And then here's an artistic rendition of the global effects associated with it. There's no arguing that it was global in its effect. There are people that want to argue that there's a lot of science that says it helped make the extinction of the dinosaurs happen. And then there's scientists that don't agree. And that's the way it's always going to be. And Gary Larson poked fun at us. And back in the day, he said the real reason dinosaurs became extinct, well, you can see for yourself. I'm not the first one to share this one. It's a pretty good cartoon. And, I'm happy to talk about that stuff at the end during the question period too, because everyone's got a good opinion about why or why not. So let's look at the importance of dating impact craters. This comes from Elements magazine in 2012. They said that catastrophic impact events have had a role throughout Earth history in the development of life and have been implicated widely in the debates about the causes of mass extinctions. So for me, that makes it quite obvious that we would want to link the age of a known impact crater to changes in biodiversity. So that's kind of like the bottom bullet there. That's the top bottom bullet. We also want to know, has cratering rates changed through time? And fortunately, they have. Early on, when the Earth first formed, we had more impacts and larger impacts, and now we have less. And when we do, they tend to be smaller. So if you look at Chicxulub 65 million years ago, 150 kilometers in diameter, compared to 50,000 years ago, it's only 1.2 kilometers in diameter. That's kind of a way to look at it. That doesn't mean we can't get another Chicxulub. That's not what that says. It's just if you look at the cratering rate, we usually don't get big ones at this point. So, and then it also helped us predict the risk of future impacts. When you look at that LPI video, you can see why we'd want to do that. And now let's see, I think we got 22 minutes on my timer to look at a couple of Group 18 results from our NSF grant study of dating terrestrial impact structures. So mainly what I did for the 2 years during that postdoc was we dated different impact structures. In some cases, they were already determined as to, through other methods, as someone had already come up with some date for that impact structure. And we wanted to use this isotopic method known as uranium, thorium, helium. And we'll talk a little bit, you've probably heard of carbon dating. Maybe you've heard of uranium lead or argon. So this is just kind of a variation on that theme. And so it's possible to use the helium 4 alpha particle to date minerals because it's a daughter product produced during the radioactive decay of uranium and thorium parent isotopes. So this lower image, I don't want to get lost in the details. We just want to look and see that thorium-232 eventually decays in a myriad of ways to become lead-208, and uranium-238 does similarly to become lead-206. And we can see, so there's, along the way, helium is made occasionally. And so you might have heard the term half-life, and that represents how much time is needed for half of the parent isotopes in a mineral to produce daughter isotopes. So we can start to use this as like a mathematical way to look at a mineral, measure what its uranium and thorium is, by dissolving it, and then also extracting helium from it. And we can see the last time it was at a certain temperature. This is another way of looking at, so here's uranium-238 is the parent as it undergoes alpha decay in that decay chain. That's only one part of that decay chain. it produces something like a thorium-234, but also the helium-4 alpha particle. So that's what we're interested in. So how can we actually use helium in a mineral to, date an impact crater? So this is a cartoon diagram. Y-axis is, as we're surface of the Earth here, temperature here is about 20 degrees Celsius. If we go to about 10 kilometers depth, we're at about 250 degrees Celsius. And then what I want to do is I want to point out, so we're going to pick a mineral that we would prefer to use for isotopic dating using this method, and that's the mineral zircon. So this is meant to be a zircon in an impact melt. This is meant to be a zircon at almost 10 kilometers depth, and this is a zircon near the surface. So at cooler temperature, closer to 20 degrees Celsius. So let's look at this one first. Zircon, yeah, it's mostly composed of zirconium, silicon, and oxygen, but it incorporates uranium and thorium. And since we know that those undergo decay, as they do, if that zircon is close to the surface, it is cool enough that the structure of that mineral is tight and compact, and helium is not allowed to escape unless it's broken. So that's what this little cartoon is meant to say. As helium is produced during uranium and thorium decay, it's captured, and it's like a clock. It's holding that information for us to go get that from it. If that a different zircon is at a depth like this, as it undergoes decay and produces helium, the helium is allowed to escape at a rate equal of it being made. So there's really no net gain. But if we also put it in an impact melt sheet like Manicouagan, we actually can reset it also. So some of the examples I'm going to show you right now, well, one of the examples that you guys are interested in Chesapeake Bay, it's not in an impact melt sheet, so it's not quite that simple, but you guys get the idea. If a zircon's hot at some point, it kind of resets the clock. If it's cooled again, it starts the clock over. And then different isotopic systems measure different temperatures. So if you look at a zircon, if you look at uranium lead for a zircon, you're actually looking at the last time it was probably in a magma, as opposed to if you're looking at uranium, thorium, helium for a zircon, you're looking at the last time it was about 180 degrees Celsius. So not quite the same. Magma is like 700 to 900 degrees Celsius. And then 180 degrees is something you can get in the crust of the Earth. You don't have to be, we can ask questions later. So if we look at, this is a sample that comes from Manicouagan. If we want to use uranium, thorium, helium, we have to take this sample, we have to crush it up, we have to find the minerals that we want to use as a target mineral. This isn't zircon, but you get the idea. I did a titanite study on the rocks at Manicouagan. So it's the same principle. You have to find the mineral in question, prepare it, and then we want to put it in, this is an alphacon. This is Dr. Thijs van Soest. He works here at Group 18. He works for KIP. So we actually worked together in 2010 and then again for my postdoc. And so we're right down the hallway from each other. So what you do is this machine right here is you can put individual minerals in a little holder here. There's a laser here that shoots the laser light at it, heats them up. And then we have an extraction line, like a vacuum line over here, that can pull off the helium and accumulate it and measure it for us. So then we would take that same crystal, we would dissolve it in acid, and we would measure it on another device to see how much uranium and thorium was in it. And then we can do a calculation that tells us the last time that zircon saw 180 degrees Celsius, which can be helpful if we have reasons to believe it. So we remember this map. This is Newfoundland and Labrador, Gulf of St. Lawrence here. So we're in Canada. City of Quebec City is off the map, but we have a large region of Quebec. I showed the Manicouagan impact structure, but now check it out. Also from orbit is this impact crater pair right here. So pretty exciting when I see stuff like that. I still get excited about that. These are known as Clearwater West and Clearwater East. So this is a ESA, European Space Agency satellite image. So the colors aren't true colors. There's some bandwidth problems here. But this dark region is lake water. This dark region is lake water. This is a ring of islands. So this is a complex impact structure. It's 32 kilometers in diameter from like here to here. This is also a complex impact structure, and it's about 26 kilometers in diameter, but you can't see the complex form because it's covered by lake water. So samples from this were harder to get because here you just get a float plane, or you get there with a float plane, you can take a hammer and just get your rock samples until your heart's content. Here you got to get drill core, and that was done in the 60s. Luckily, we got some material from there. So I want to take a second and say, scientists know, astronomers know that some asteroids circle each other, or they're in orbit around each other. You can have doubles, or you can have even more. So sometimes you see on other bodies, you see doubles. Sometimes that double is a result of a single asteroid breaking before hitting, or you can actually see chains. And so they're known to be seen elsewhere. It's been known for quite a while. And then this is that famous image, one of the famous images from Shoemaker Levy 9. So Carolyn and Jean, they were looking through a scope with Levy, and they were waiting on this comet to come back, and they took an image, and they said, hey, that's weird. It doesn't look like the focus is right. So let's check our focus. And they looked at it and they took another image. And they're like, no, the focus is right, but the object is still fuzzy. And then as it got closer, they realized it had been tidally disrupted by getting too close to Jupiter and its moons, and it had been broken into at least 22 different fragments. So there's ways to get doubles and chains of impacts on a planetary surface or a moon surface. So if we go back to this, the early idea about, so this is in Canada, the teams that went out there, Clearwater West has been dated numerous times, and the results always came up at about 280 million years old. And the earliest result for Clearwater East was done in 1981. It was Reimold, and he did rubidium strontium. So not all isotopic systems behave the same way, or as well behaved, or as predictable, or as accurate. So it's not trying to say any of them are necessarily worse or better. You just have to know their limitations. But this was interesting because 287 was pretty close to 280, and that means it was a double, right? It just made sense that they're so close to each other, they must have came in as a pair. Later research, 1990, came up with an argon-argon result of 460 million years. They were doing a number of craters at the same time in Canada, and they quickly just kind of like talked themselves out of the result and said that it was most likely excess argon, and that's why they got an older date. And they said, yeah, we don't really need to, we don't want to stick by this result. We feel that the 287 result of the earlier work was more accurate. We still believe it's a double. We don't know what went wrong with our research. Well, another group, you guys remember Martin Schmieder's hand on the building stone in Bavaria. He did a paper in 2015 where they redid argon-argon work, and they were they paid a lot more attention to what they did. They didn't get astounding results that were really, really accurate, but they came up with a similar result. And they started looking at other things that didn't match between the two craters being formed at the same time. So they, we felt kind of bad in a way that we were waiting on sample material for this. So needless to say, we were a little bit late to the presses, but it was in a way it was good because Martin did such a good job arguing why it wasn't just the date that mattered. There was other things like remnant magnetism in the impact melt. The east melt sheet has a component of the projectile that can't be found in the west. There's arguments here, but it was interesting. So lo and behold, our work in 2016, we ended up publishing the helium. So two different systems agreeing, they're both noble gases. It was pretty neat. They were doing theirs on a melt rock, and we were doing ours on zircons. So that felt pretty good. But like I said, it comes from a melt sheet, so it was a little bit easier to kind of see that. If we look at this kind of same thing again, the same little sequence or scenario for Chesapeake Bay. So this comes from 2019. We did a presentation at GSA here in Phoenix, and then we also we published. And what's interesting here is, so this isn't at the crater. This is ejected material. And so that's something that isn't as well understood or known, and it's a lot more haphazard if you think about it anyway. the luck of you finding what you find on the sea floor has a lot to do with it. And so luckily, the drill cores that we ended up obtaining sample material from were found in the 80s. So, and luckily there was some sample material left. This name right here, Walter Hale, he was reluctant to give us the remaining sample material, but he asked, he's like, can it be useful? And we felt it could. And we've actually got science out of it, good science out of it, 2 different ways. So you guys know where Chesapeake Bay is at. And look, I got you guys on here. So Natural History Society of Maryland is right there, pretty far away from the crater, but not too far away from the crater. And then we got 2 things going on here. This outer diameter is not the actual rim to rim diameter of the impact structure. So one thing I like to point out to people is, so Chesapeake Bay is not an impact crater, right? But underneath part of it is this 40-kilometer diameter impact crater that actually occurred in a seawater sequence. So it hit seawater and it hit soft sediment. So it didn't do the same thing that it would have done had it done it on land. So anyway, that's what this image is meant to show. And then here's another map, still looking at Chesapeake Bay. We got North America, we got the tip of South America, we got the Atlantic Ocean, we got the Pacific Ocean. So here's that ocean drilling project, site 1073. More than one hole was drilled there. So our sample material came from hole A. We see Chesapeake Bay impact structure located right here. And then we've got this red envelope here. And so someone asked me what a badiacite was, and that's where we're going here. So Chesapeake Bay impact structure is one of the few impact structures out of 200 known on Earth that have produced glassy objects that have landed elsewhere away from the impact site. Now, in some cases, fortuitously, like Chesapeake Bay, the source crater has been located for these glassy objects, and they can be dated also. So that's one of the things that, the chemistry of these glassy objects and the date of these objects can be related to the source crater. That's how they kind of relate it to the source crater and figure it out that they're actually tied together. So badiacites are glassy tektites that are found in Badias, Texas. And interesting, on the personal note of inspiration for me, I was living in Louisiana at the time, and I wanted, I read about these tektites that had been thrown out of Chesapeake Bay. I didn't have much to do in Louisiana that was fun with a rock hammer. So I was driving over to Texas and trying to find these on my own. So it took a few times, and I got some help from other people and finally found some. But again, if you find this kind of stuff interesting, check it out. There's also glassy objects found in Georgia known as Georgites. Here's the sample material. It's not a rock. It's just kind of a sediment. We pulled 21 different zircons out of here. Some were shocked, some weren't. We tend to like a certain size of a zircon crystal for doing uranium, thorium, helium, and we don't like fragments. So let's look at shock metamorphism in some of these crystals. So left side image here, it's kind of fuzzy, and it's got this weird striated gold. What it is it's a piece of sticky tape that has a gold foil on the back. So I don't lose that zircon. I don't want to lose that zircon. So what you can see here is it's fairly small. We said there's 1,000 microns in a millimeter. So that's 73 microns by 43 microns. But what we can see is it's clear. And then same thing here. This is a fairly small one. It's fairly clear. And then when I look at it under the scanning electron microscope, we don't see any real damage. It's got a fracture right here. It's got a fracture right there, but it's not the kind of damage we're looking for when we start talking about shock metamorphism. So here is a broken zircon. You can see it's more rounded, almost like it might have been melted. And then we see a cloudy zone here and a cloudy zone here. If we zoom in, this is scanning electron microscope. If we just kind of like manually blow that up, we see 2 different directions of planar deformation features. So that fragment was shocked. There was one fragment in here. It's poor quality, but you can see it's quite cloudy. It's a little bit bigger than the other 2. And then we can see under the scanning electron microscope, there's some zircon material, but a lot of it has actually decomposed to a mineral known as bedelliate. And that occurs at very high pressures. If you look right here, So Alex Whitman, he was the first guy to ever ask me a question at a conference in Houston. He actually did some studies and realized that shock pressure, that's a very high shock pressure of 90 gigapascals is required to make that happen to zircon. So some pretty good shock metamorphic effects, but not necessarily in the pieces that we dated. We wouldn't really want to date those, but it gave us an idea of characterizing the zircons in that sample. So when we look, this is the 8 youngest that we dated out of the 21. And you can see, like, here's a real clear one, and then we see some cloudy ones. And what I want to do is I'm right at the end of the talk. I want to kind of relate these to the dating result. Instead of looking at each of these date, we can look at it on a graph. So a probability diagram, probability as it gets higher is greater. And then we see x-axis is 0 to 200 million years. So we have some things that are quite old. Our estimate for the impact for Chesapeake Bay is based on 2 of these grains, and we come up with 32.5 million years for that impact. And that's in pretty decent agreement with most of the other work that's done. And then we can kind of look at, there's reasons why we don't want to put this in there. And since it's not an impact melt sheet, we can look at the shock metamorphism or lack of shock metamorphism in these and see why we wouldn't pay attention to them. So like this one looks like it's never been part of an impact. It was probably just sitting on the seafloor when the ejecta arrived. And then, but this one looks pretty cloudy. But even though it looks that cloudy, it didn't get fully reset. That's sitting at about 73 million. So, you know, that's another thing that it's explaining to us that, okay, it's fairly easy to reset the helium system compared to something like lead, but it's not so easy that all of it got reset to the exact impact age. There's also like an oddball right here, and that's this one. It looks very euhedral. It's very well shaped. It doesn't look cloudy, and yet it's very close to the impact age. And so you have to look at these things. You have to come up with your reasons of why you add them to the average or why you don't. And in this kind of scenario, it's a little tricky. I wouldn't bet my house on it, but it's still an interesting result. And it tells us something about the uranium, thorium, helium system. I'll say another thing more interesting than the dating result was this gentleman in Australia noticed that paper, Aaron Cavassier, he works at Curtin University in Perth, and he wanted to get a hold of this fragment. And it's kind of interesting. He was really excited about that pressure, the shock pressure for decomposition of bedelliite, but it didn't work out for him. We sent him this one, and we also sent him one he didn't ask for. And that ended up giving him some exciting information on shock metamorphism to zircon to a different mineral known as reedite. So reedite has been seen, but the lucky thing about this piece of ejecta landing in seawater was it froze the shock effects fairly quickly, and it wasn't allowed to stay in a warm environment and relax back to a different form. So he saw kind of like a snapshot in time where he thinks he understands how reedite forms and not just that it exists. So this is an interesting paper. You would probably, this would be good for you to read if you want to go to bed. So, and that puts us at, I think, so we talked about a lot. We talked about why studying impact craters, you know, from the society perspective is important. Talked about how they form on the surface of the Earth. It's obviously similar on other planetary bodies. Amount of gravity is different. We looked at 2 basic types, but we also saw kind of like a third type. We started getting into the complex morphologies sometimes they have rings and not just a central mountain. We looked at, there's only about 200 that have been detected and or proven on the surface of the Earth. A lot have been erased and or not found yet. Looked at the one near miss from 2013 at Chelyabinsk. There's another one from 1908 in Siberia, Tunguska, if you're interested in that. That one actually killed some animals and fell a lot of trees in a forest. And then we looked at that short video, asteroids do still pose a threat. And then we looked at 2 examples of how Group 18 here at Arizona State University School of Earth and Space Exploration looked at Clearwater West and East, and then also Chesapeake Bay. So I say thanks to my colleagues. Thanks for your attention.
Thank you so much, Mark. Can you come stop the share and we can all come back together and then get some questions for you?
You bet. I got to undo my pointer. There we go.
All right. Well, that was wonderful. I knew that was going to be great, and it did not disappoint. Thank you so much. Do we have any questions for Mark? Let me see. Nick wants to know if you can find tektites in Maryland from the Chesapeake Bay bolide.
I know of one. There's yeah. I've heard of one being found, but not a lot. If you go, if you go do a search at Chesapeake, like Earth Impact Database, and look for tektites, you can see different maps of all the known locations. So I think they have been found, but they're not very easy to find. And so I don't think you're going to find much joy trying that. I think a lot of people have been excited about that kind of thing. And so if it was something that was fairly doable, you would see results like on the internet. You'd see someone with their own samples somewhere or selling them. And you got to be careful about things you might buy that are stated to be those kind of objects. There's a lot of people that peddle meteorites that aren't meteorites, and a lot of people that peddle tektites that are not tektites.
Jean wanted to know if I'm saying this correctly, if they extrapolated to the oceans and to the land that is forested or covered by glaciers now, would the actual number of impacts be 2,000 to 6,000 over some period of time?
Let's see.
It's kind of up and
Oh,
down.
well, I mean, I look at it like this. We've had thousands of impacts. Yeah, for sure. They're no longer visible. So it doesn't mean they didn't happen. So if you look at having an atmosphere, that cleans out some of them. It prevents some of them. So if you look at Venus, and you look at the size and the size, the size distribution of impact craters on Venus, they tend to have pretty large craters because they have a very thick atmosphere. So for it to get through, it's got to be pretty big. So if you look at the surface of the Earth and compare the atmosphere we have to the moon not having an atmosphere, yeah, so the moon records smaller micro meteorite impacts that we don't because they burn up in the atmosphere. So, but yeah, we've had thousands of impacts. They're just no longer recorded on the surface of the Earth because the surface of the Earth is, in many cases, recycled or eroded to the point where, so you have to look at it that way also, that you can have an impact crater, and then over time, if there's erosion occurring, you can erode that material out. So you might find shock metamorphic effects in a riverbed that you can't find the crater for. That's been seen also.
And George is mentioning the Carolina Bays again that we've talked about a little bit earlier. The younger, driest impact hypothesis. Does that ring a bell to you?
Yeah, these things kind of come into fashion and go out of fashion. I'm not saying whether it's correct or not, but the interesting thing, when Chicxulub first kind of hit the scene, then people started looking for correlation between other extinction events and impacts, and that's where dating becomes important. And so sometimes there is evidence found that starts to support it or somewhat support it. I remember seeing some like fossilized bone with meteorite damage on it, and I might be associated with that. So I think there's some interesting things out there, but normally through the test of time, you guys might have heard recently that there was a big impact structure under part of Greenland, and that was big news for a while, and then it's kind of fallen out of favor. A lot of the quote stuff that was reported is deep metamorphic effects or whatever. I don't even know all the details, so I don't want to speculate on that. I've heard of the Clovis comet. Those are interesting things to look into, and then if the science is good enough, they'll end up in other places, or they'll end up supported by other researchers. So I don't know on the Clovis comet. Comets are a little bit difficult also, because I don't think we've actually found an impact crater where we can say we know it was a comet. And they're more of an icy body. So I'm not quite sure the damage that they do compared to iron or stone associated with asteroids. But one of the things that if you ever get a chance, look at the SOHO instrument, Solar Heliospheric Observatory from NASA. Maybe look up Comet Lovejoy and the video of it going around the sun. Comets definitely pose a threat. If you look at what happened to Jupiter during Shoemaker-Levy 9, we're happy that didn't happen here.
George wanted to chime in.
Yep.
Can you hear me?
Yep.
Great. One of the things about the Younger Dryas impact is said that comet, if it was a comet, hit on the Laurentide ice sheet. And when it not only blew up the comet, but it blew up chunks of ice out of the ice sheet also. And they theorized that's what caused the Carolina Bays, because of the angle of impact. I'm not pro, for, or against it, but since that theory came out about 2006, there's been tons of debate both directions. It's very interesting to follow.
Yeah, I agree with you, and I find the shape of those bays very interesting. They have a lot of a directional feel and a scalloped feel, and I think you should keep interested in that, and because I don't know much about it, so I'm not saying that there isn't a tie. I think what's kind of interesting about following this stuff is you start to get a little bit critical, not in a negative way, but you just start to kind of evaluate who you agree with and why, and not, so yeah, I think there's people out there that have good arguments for parts of this. Pardon?
Yeah, I find it very interesting, the discussions that go back and forth in the different papers they publish.
Yep. I would suggest if you hadn't read T-Rex and the Crater of Doom, check that out. It's a very short read. It's a fun read, and it's just the start of what you can kind of check out online. And someone was mentioning the recent studies from the drill core in Chicxulub. So yeah, there's a lot of neat stuff. Go ahead.
Sorry, Thomas says, was there an impact in Russia that hit an area of coal and converted it to diamonds that were mined?
Yeah, so I've heard of impact diamonds are proven, but my understanding is they're very small.
George?
Yeah, that's said to be the parallel crater of the Chesapeake Bay bolide. It like the Chesapeake Bay crater was part of a larger body, and it split up when it hit the atmosphere. Part of it is said to have hit about 100 miles east off of Atlantic City, and that's called Tom's Canyon. The largest fragment hit over in Western Siberia, and it's credited with causing a minor extinction event called the Grand Cratering that wiped out most of the mammal life in the late Eocene of Europe. And that's the crater that's said to have formed the diamonds.
Mm-hmm. Which crater is that?
It starts with a P, like Popagai, something like that. And I was watching something yesterday on it, and they say it's very hard to research because the Russians don't want people to come in and interfere with the diamond industry that they have.
Yeah, well, like I said, my understanding is, that was an exciting thing to kind of hear when it first happened, is that there was diamonds, but my understanding is they were quite small. So yeah, and I'm not arguing. I'm just kind of telling you my poor memory of that aspect.
I appreciate that.
Hey, Mark, with the advent of Google Earth, are there any community sciences and science projects where you have folks looking at different parts of the globe trying to identify impact craters?
That's a very good question. I remember a number of years ago, it's probably almost 2 decades ago, or at least decade and a half, where they were letting people, there was like a website that you could sign up as a user and you could help look for effects on the moon. And so yeah. And so like that kind of idea is out there. And I've had people reach out to me, you know, that, hey, I've found these circular features or whatever. But the main problem there is, you know, time is money and access, you know, so it's kind of like if it's close and if someone sent me a picture of a true shatter cone and they could show it in situ, meaning in the ground, along with other shatter cones elsewhere, I'm sure they would get visitors. But that's often not the case.
So if we're out there looking at things, what should, I mean, there's still a lot to see and discover and be a part of that exploration. Is there, we should be looking for shatter cones and those kind of indications on rocks?
Well, it's a good question. So when I was in Louisiana, I made kind of a little tour of here's where I'm going to go in Texas. The places that were reported as impact craters, not all of them were. So sometimes they were just small collection sites for, you know, bits of meteorite. Like I said, you can go to a place that's a pit and it's not really a hypervelocity impact crater. You know, they found a fragment of a meteorite there, and there's like a depression, but not because of hypervelocity impact and excavation and modification. So I would say go to something like the Earth Impact Database, look for ones that you can find lists of ones that haven't been proven or ones that were proven and then were taken off. And I would say one of the things, if I can share for a second, a book that you might want is like, let's see here. Traces of Catastrophe is a PDF that you can find online at Lunar and Planetary Institute. You can download the whole thing. They used to have it for free. You just send them shipping and they'd send it to you in paper copy, but it got gobbled up. And then Bev in French, like I said, so this got a lot of people excited. It'll show you what's known about shock metamorphism from back in '98, but it's still, you know, it's still relevant. And then he did that paper with Christian Kerbel in 2010 to say, you know, so if you want a copy of that and you don't tell anybody I gave it to you, you know, send me an email. That's here. There's my email address. Those 2 papers will get you started as to, you know, the thinking behind how they found the ones that are known, and then how people go astray on not finding real evidence. There's things out there that look like shatter cones that aren't shatter cones. And then it's tough to properly ID. So I think the Greenland and other craters, you know, that Greenland crater, they found minerals that had things that they interpreted as planar deformation features, but it didn't hold up when other people looked at it. You know, like they want to see a number of grains. Like I said, there's a special apparatus that goes on a microscope, an optical microscope, that helps you read all the different angles, and you end up twisting this thing in multiple planes, and you count how many you find, and you do statistics on it. And so it's not as simple as just going, oh, I looked at it under a microscope, there's some lines in it, and that's good enough. So yeah, but if you find something like a shatter cone or a fragment of the meteorite, or in some cases, the impact melt that's left behind has meteoritic a component, you know, so yeah, I think there's a lot to be excited about. I think the Carolina Bays is the neat thing about the Carolina Bays is that someone hasn't come up with a conclusive yes or a conclusive no. So it's still kind of intriguing. I had a guy that if you look at the large impacts on the surface of the moon, those the mare, the darker regions. He had an idea that was caused by asteroids that got close to Earth, and then the gravity of the Earth made them go into the moon, which that doesn't hold up very well. But I still found it intriguing because like I'm kind of, this is my second career. It's not my first career, and that's why I say be inspired. Don't let people tell you no until you've kind of looked at it yourself and you feel the evidence tells you no. Eugene.
Gene has his hand up.
Yep.
Two things I couldn't resist. What was your first career? That was-
Military. I was in
okay.
the military, yeah.
And what part military?
Air Force.
Okay. And
I didn't have to work hard.
and the second thing is that you talk about different explanations for formation of variety of structures, and the method of multiple working hypotheses arose in geology, in which you look at the range of plausible explanations for something without favoring one as your child, and then that spread to biology, and it seems that ever since it's completely ignored by some people in both fields who just have their pet theory and want to push it for an area. And then in other fields, people really go on, such as yourself, looking at the variety of evidence. How many ways can we figure this out? Which isotopes, and is it a gas, or you're looking at lead, or you're looking at uranium, thorium, right? And a variety of other things. So it's neat to see that. And you're being, so calm about it. And the same is true of George. George is calm and recognizes a variety of explanations. So, and we haven't had any true believers who wanted to push their theories about anything here yet. So.
Yeah, I think, it's a good point that you make. Having come to geology, it was interesting. My first experience at the University of New Brunswick, I met some really wonderful people. And I also saw some people where their ego was so much of their job that it wasn't fun to be around. It felt like being in 4th and 6th grade again on the recess field when you were having a fight with somebody. And I've learned to make a lot of mistakes myself. And one of the things that was great about my supervisor was he let me make mistakes. And I can totally accept that I got something wrong, or that I didn't understand something, because that's the other thing too, is I'm not the sharpest drawer. There's not the sharpest drawer out of the knife. But yeah, so it's, for me, this has been a lot of fun. It's been great learning. I could probably use to pay more attention, more calm attention when I do things instead of get so excited. But yeah, I think that's half the fun, is being part of the discussion, as long as it's semi-polite and respectful.
And Mark, one last brief from me. I mean, I don't want to, but are people going back into the collections of rocks and minerals that are in natural history society, in natural history museums, and taking a different look at them, using the technologies that we have now to try to extract new data and understanding?
Well, that's what they do. That's what they do with lunar samples. Yep. They try and earlier samples they tried to kind of like compartmentalize it and not eat it all up at one time. And that's a very good point, that as technology advances, we are able to do things that we couldn't do 40 and almost 60 years ago now. So luckily, Clearwater East still had some melt from the core and some good zircons in it. Luckily, Walter Hale was nice with that last bit from the drill core from 1073A for Chesapeake Bay. And I think better than the dating result was Aaron Cavassier's realization that there was a snapshot in time for that one crystal. It was kind of funny. I got that one crystal off, put it on the tape, and I looked. I had 3 of interest. And I said, I know he didn't ask for this, but I'm going to take this second one, put it on there. And that has nothing to do with intellect or anything. That's just dumb luck. And when he got the first one that he thought was so sexy, in that first publication, he put it on some epoxy. He tried to process it, tried to get it under his instrument. It didn't work out. And then he went to the second one and saw something he completely didn't expect to see. So that's, that's how it works. I think that's the neat thing is a lot of you are pointing out, you just stay interested, keep some momentum, and good things happen from that.
Well, this has been wonderful, Marc. Thank you so much for taking your time and sharing your knowledge and expertise with us tonight. You've given us a lot to think about, a new way to look at our world and our Earth and our minerals that we call home. And thank you all for joining us this evening. We hope to see you soon at one of our upcoming Zooms and in person. We have our next in-person thing is August. We're doing Shark Fest, so we're in the middle of planning for Shark Fest. But we'll see everybody soon. Stay safe, stay curious, stay outside, and we will be in touch. Take care, everybody.
Yeah, thanks everybody. It was great. Thank you very much. It's been a nice discussion, a nice group.
Am I the only one who noticed the face in one of your images? In Clearwater East?
Oh, okay. Yeah. Was it in East or was it in West?
It was just the two craters that are together, and it's just north of one. If you could bring back can you put that slide back up for just a second?
Just a second. Let's see. Oh, okay. The nose.
Well, I thought it was an entire face, but
Where is that?
He's looking at just north, just on top of the crater in the vegetation. I'm looking at.
Oh, okay. Interesting.
sorry, I don't have a mouse at my disposal. But yeah, there's a nose, there's two eyes, there's a mouth below the nose. You just go due north from there.
Yeah, that's an eye.
Okay.
There's two eyes. You mentioned the nose.
Okay.
Interesting.
You're on the nose, and there's a mouth below it. And the face even has an outline around it.
Yep. Okay, I get you. Yep. The man in the moon.
He's
Right.
He's right there at Clearwater.
Yep.
The man in Clearwater.
You stare at these things for too long, you miss the obvious stuff.
Yeah. No, this is great. I will get in touch with you tomorrow, Bronwyn. Thank you for reaching out to me. I will get some raffle tickets, and I think my sister would love that mug.
Great.
Don't wait on the raffle tickets. Raffle ends in May. Ends
Okay.
at the end of May.
Yeah,
Good, fantastic talk, by the way.
Thank you, guys. Thank you, everybody.
Thank you, everybody. Thank you, Marc. Take care.
All right, see you later.
Bye-bye.
Thanks, Bronwyn.